In this video, we look at how to handle higher degree polynomials, including quartics and above. We're also going to look at the difference between odd and even functions, and how you can prove if your function is odd or even. For those who don't know me, my name is Chris Iannazoni. I used to work as an engineer for a defense company, and I've since left that to start a career in tutoring. I make these videos so that VCE students can do the best they can in math methods. With that out of the way, let's get into it. The first thing we'll do is look at the difference between odd and even polynomials. Consider the generic polynomial below. We know from our earlier studies that if the power was 2, then this would be a quadratic, in which case you would now have a turning point form. We also know that if the power was 3, it would become a cubic, in which case we would have an inflection point form. This actually generalizes further. If your power is odd, so 3, 5, 7, 9, then you're always going to have an inflection point form. The only difference between each of these forms is the steepness of the curve. As your power increases, the steepness also increases. If your power is even, then you have a turning point form. And once again, the only difference between the powers is as they ascend, so too does the steepness of your parabola. Let's look at some examples. In this case, our power is 4, in which case we have a turning point form. The x plus 1 means that we're shifting to the left by 1, and the plus 2 at the end means that we're shifting up by 2, giving us a coordinate of our turning point to be -1, 2. If the power was instead 7, then that point would now be an inflection point. And since it's a positive cubic shape, it's going to start at the bottom left and at the top right. The idea of an odd or even function is a little bit different because it's not specific to polynomials. Odd or even functions are those that meet the following criteria. We're going to look at a few examples. We can prove that any function is odd as long as f of negative x is the same thing as negative f of x. So if we're going to try and prove this, then the first thing we're going to do is figure out what is f of negative x. And we do that by replacing every x in f of x with a negative x instead. When we do that, we can actually do a bit of factorizing to take that negative sign out the front of the term, since any odd power term allows you to do that. Once we've achieved that, let's try and find negative f of x, which just means we take f of x and then slap a negative sign at the front of it, and all we're going to do from here is distribute that negative sign all the way through. And when we do that, we see that f of negative x is identical to negative f of x. Therefore, we've proven that our function is odd. We do a very similar thing for even functions. All we're trying to do here is prove that f of negative x is the same thing as f of x. So once again, we're just going to figure out what f of negative x is by replacing every x with negative x. In this case, because all the powers are even, the negative terms inside the brackets cancel out. From here, there's not much else to do. If you have a look at f of negative x and compare it to f of x, you'll see they're the same thing. Hence, we've proven that that function is even. From your prior studies, you should be familiar with how to sketch the factorized cubics. There were 3 main things you had to watch out for. The first was the sign of the x cubed term, which would tell you the overall shape of the cubic. The next were linear factors, which were always x-intercepts, and the last was repeated linear factors, which were turning points. We're just going to dive a little bit deeper into this to revise the rules such that they apply to all polynomials instead of just cubics. To start with, linear terms don't change. They will always cut the x-axis. The difference occurs when the linear terms have powers. If your power is even, then that term will always be a turning point. If the power is odd, then that term will always be an inflection point. The next thing to worry about is that not all polynomials have a cubic shape. Some of them have a parabola shape. If your highest power is odd, then you have a cubic shape, in which case there are 2 possibilities. If your cubic is positive, then it's going to start at the bottom left and at the top right. If your cubic is negative, then it's going to start at the top left and end at the bottom right. If your highest power is even, then you have a parabola shape, in which case there are once again 2 possibilities. If you have a positive parabola, then you start and end at the top. If you have a negative parabola, then you start and end at the bottom instead. I know that's a lot of information, so let's have a look at an example to see how it all ties together. To start with, the x-intercepts are solved as normal, using null factor law. This polynomial has 3 unique terms, and so we're going to have 3 unique solutions. X equals 1 is a cut through the x-axis. X equals -1 is actually an inflection point because its power was odd. And x equals 5 is a turning point because its power was even. The y-intercept is also nothing special. We're just going to sub in x equals 0 and solve. Now, when it comes to finding overall shape, we need to figure out what the highest power in the function is. That'll tell us if we have a cubic shape or a parabola shape. We do this by counting the number of x terms. The first term has 1x, the second term has 5x's, and the last term has 4x's. That's 10x's total, which is an even number. Hence we have a parabola shape. Furthermore, it's a positive parabola shape, hence it's going to start and end at the top. The graph will thus look something like this. It starts at the top left and then inflects at x equals -1. Then it goes through the y-intercept before circling back to cut through at x equals 1. And lastly, it's going to dip back down so that it can turn at x equals 5 and then finish at the top right. That's all you need. Just like when it came to cubics, you didn't have to find those other turning points. Even if you did know calculus, trying to solve the derivative of this kind of function would be well beyond the scope of what math methods will ever give you for a tech-free. If you found this video helpful, then you should consider joining my free community. I host a Q&A call every week to personally help you through any of your specific questions, and you'll also get access to more resources like this, including written and recorded lecture content, as well as practice exams and SACs with detailed solutions. It's pretty cool, you should check it out. I'll see you there.